Okay, this is the um, this lesson is going to be about lattice enthalpy. Okay, so what this refers to is looking at the 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 energy required to break up an ionic lattice. And so the lattice enthalpy can either be described as lattice enthalpy formation, and for sodium chloride that would be Na ions in the gaseous form and chloride ions in the gaseous form, the energy change when they form sodium chloride solid. And the lattice enthalpy of dissociation, dittos, is the opposite of that. It's NaCl solid going to Na ions in the gaseous form and chloride ions in the gaseous form. No, it's probably no surprise to you that this here would be very endothermic. Okay, sorry, very exothermic, and it has a value of for sodium chloride, it's minus 780 kilojoules per mole. And of course, this process, this one here, is going to be very endothermic. You're going to require lots of energy to break up the lattice, aren't you? So if you just remember your ionic lattice, if I just draw a two-dimensional, there's a sodium, each sodium ion is going to be surrounded by chloride ions. Draw them a little bit bigger, as they are a bit bigger than the sodium ions. Okay, and then there's going to be sodium ions there, and that's going to be a repeating structure, yeah? We're all familiar with that from year 10, really, at least. Okay, so when you break up that lattice, you're going to have a strong attractions between the positive sodium ions and the negatively charged chloride ions. So to separate those two, you're going to have to put a lot of energy in to separate them. You're going to have this force of attraction between them. So this is going to be very endothermic, and that's going to be the opposite value. It's going to be plus 780 kilojoules per mole. So when we talk about lattice enthalpy, really, we should always say, is it lattice enthalpy of formation or dissociation? But it's going to be the same value, just one is going to have a negative sign, one's going to have a positive sign. Okay, so that is the definition of lattice enthalpy, and in later videos we'll talk about how you can calculate that from experimental data. But today we're just going to have a little think about the magnitude of lattice enthalpy for different ionic compounds. Okay, so I've got a table here ready to go. Right, let's have a look at this table first. Just outline it in green. Okay, so what we've got there, we've got the halides of sodium. Okay, so in each of those we are going to have a sodium ion, and we're going to have a negative ion that is attracted to. So I'll just draw the fluoride there, the first one. Okay, and what is happening as we go down here? Well, we're obviously going down group 7, aren't we? The halogens. So the size of the sodium ion is going to remain the same, but let's think about the halogen ion. Well, that's going to go, fluoride is the smallest, chloride is a bit bigger because you've got another shell, haven't you? That's the electronic structure of fluoride is going to be 2,8, chloride is going to be 2,8,8, bromide a bit bigger still, and iodide biggest of all. So let's have a look as we go down there. As the negative ions get bigger, quite clearly, right, the lattice enthalpy becomes weaker. Now, there's no sign in this table here, but of course, if it was dissociation, there'd be positive. So let's think about dissociation. So why do you require less energy to dissociate sodium iodide, then you do, let's see. So if you look at sodium iodide, yeah, you're 705 kilojoules per mole, whereas for sodium fluoride, you need quite a lot more, 980. We've got a clear trend there. Well, you can probably guess what's going on. Is right. There's a couple of different ways we can think about it. But first of all, let's think. Right, there's an attraction between these two, isn't there? Yeah, they are going to attract each other because you've got opposite charges, electrostatic charges. In the case of sodium fluoride, the attraction is going to be stronger than with sodium iodide, because if you've got iodide there, it's much bigger ion, but it's only got the same amount of negative charge. It's got one negative charge spread over quite a bigger volume of ion there, and so it's not going to be so strongly attracted to the sodium. And that accounts for the trend that we see here. You know, as we go down, the lattice enthalpy becomes weaker. The negative ion is always the same, -1, but it gets bigger, so that its negative charge is more spread out. It's not so strongly attracted to the positive sodium. Okay, if you want to do that a little bit more formally, then and you don't need to know this equation, but if you do physics, this will not be new to you. We've got this equation here. The force of attraction between two charged objects is equal to 1 over 4 pi epsilon. Okay, epsilon naught, and epsilon naught is just a constant. So don't worry about it. So this whole thing is a constant. 1 over 4 pi epsilon is a constant, multiplied by Q1, which is the charge on the positive ion, on the positive object, Q2, which is the positive charge on the negative thing, divided by R squared. Now R is the separation of the charges, okay, the distance. Q1, that's the charge of the positive ion, or the negative, doesn't matter really, measured in coulombs, and that's the charge of the negative ion, measured in coulombs. So you can see in this case here, where we're looking at the sodium halides, well, let's just rub that out, give us some room. We can see here that the force is proportional, right? 1 over 4 pi epsilon, that's a constant, so we can forget about that, yeah. And Q1, Q2, that's a constant because the sodium ion is always +1, obviously, and the halide ion is always -1, so that's a constant as well. So the force of attraction between the two ions is proportional to 1 over R squared, where R is the separation of those two ions. So if I just draw sodium, here's sodium fluoride, and I'll draw sodium iodide here. I'll do it up here. So what is R? Well, R is this distance, okay, from the midpoint of the sodium to the midpoint of the fluoride there. That's R. Well, you can see R for this one, for the sodium iodide, is going to be much bigger, or quite a bit bigger, because the iodide's got the iodide ion has got a bigger radius, isn't it? So that's going to be R there. That distance there, that distance there, that's R. So it's bigger in the case of the sodium iodide than in the case of the sodium fluoride. So that is why the lattice enthalpy of sodium fluoride is bigger than that of sodium iodide. And because it's R squared, you know, that it's not just 1 over R, it's 1 over R squared, isn't it? So it actually makes quite a lot of difference. Having the ion just a little bit bigger is going to, you know, because you square it, it makes a difference. This value of R squared is going to be a bigger value in this one. That's going to make the force of attraction between the to ions weaker, and that means you're going to have to put less energy in to separate the ions, to separate the lattice. Okay, let's now have a look at this one here now. Okay, this I'll just put that in green. And I'll rub out this, make a bit of room. Okay, we've got right. What we're doing as we're going down, this group here, then we are going. We can see we're going down group 1, aren't we? So the group 1, the alkaline metals, they've all got a positive 1 charge. So you have a little lithium ion, Li, sodium, bigger because it's got an extra shell, 2,8. Potassium is going to be bigger still, 288. And when you get to rubidium, you're now in the even the 4th shell is occupied, and cesium even bigger still. So the ions get bigger as you go down. Okay, as you go down the group. So here we've got our equation again. The force of attraction between the 2 ions this is a constant, so we can forget about that. Q1 over Q2 is a constant because the positive ion is always +1, and obviously fluorine is always -1. So once again, we can say that the force of attraction is proportional to 1 over the separation of the ions squared, R squared. If we think about the sodium fluoride, lithium fluoride, sorry, I'll do that here. Lithium fluoride, and I'll just get rid of these, and we'll just do rubidium fluoride. So the fluoride ion is the same size. Okay, let's look at the separation there. So the separation from the midpoint here. There we've got R. Quite a big separation between the rubidium and the fluorine. And with the lithium and the fluorine, the midpoint of that one, the midpoint of that one, R is a lot smaller. Okay, so, right, if R is smaller, R squared is going to be smaller, so the force of attraction is going to be bigger in lithium fluoride, stronger force of attraction than in the case of the rubidium fluoride. That's going to be a weaker force of attraction, so you're going to require less energy to separate the rubidium fluoride lattice than you are the lithium fluoride lattice. That, to me, that's all fairly commonsensical. As I say, you don't really need to remember this. You don't need to remember this equation, but if you do physics, you probably do remember it anyway. And right, it's just about the separation of the ions. Right, now let's have a little think about what's going on here. Okay. Now, if we compare magnesium chloride to sodium chloride, the lattice enthalpy is much bigger here, isn't it? You've got a little 780 for the sodium chloride, and a really big 2,526 for the magnesium chloride. Now, what's going on there? Right, that's a little bit more complicated, but not more complicated, and we're going to just think about our equation here in blue again. So give ourselves a bit of room. Right. Now, the lattice, the way the ions are arranged in magnesium chloride is obviously more complicated than the sodium chloride because you've got 2 chlorides for every magnesium. We're not going to worry about that. We don't really need to worry about that. But let's just think about the charges of the ions. So magnesium is Mg2 plus and Cl minus, whereas sodium is obviously just 1 plus and Cl minus. So you can see that Y is the force of attraction between the magnesium and the chlorine is going to be bigger than that one, because for the magnesium, right, force is proportional to Q1 Q2 over R squared, or for the magnesium, the positive ion, that's +2. Whereas for the sodium, it's only +1. So that alone should make, so that means Q1, Q2 is going to be twice as big. So we'd expect the lattice enthalpy of magnesium chloride to be at least twice than that for sodium chloride. And let's look at the numbers there. So magnesium chloride 2526, sodium chloride is 780. Right, it is way bigger than 2 times, isn't it? So it's not just about the charge on there, and there's something else going on there. Well, what is the other thing going on there? Well, it's this, isn't it? It's R. What can you say about the size of a magnesium ion compared to a sodium ion? Right, magnesium ion, Mg2+, the electronic structure of that is going to be 2,8. Sodium ion, the electronic structure of that is going to be 2,8 also. So, but the magnesium is a lot smaller. Why is it smaller? Why is the radius of the magnesium ion smaller? Well, magnesium has got 12 protons in the nucleus, hasn't it? Sodium's only got 11, so it's holding all those electrons in tighter. So the magnesium ion is going to be smaller than the sodium ion. And we've said before, force is proportional to 1 over r squared, where r is the separation of the ions. Well, the separation in magnesium chloride is going to be smaller because the magnesium ion is quite a bit smaller than the sodium ion. So that also is going to make the lattice enthalpy bigger for magnesium chloride. So magnesium chloride value, magnesium chloride lattice enthalpy is quite a bit bigger than the sodium chloride for 2 reasons. One, Mg is a 2+ ion and Na is only 1+. And secondly, magnesium is smaller than sodium, so that means the separation of the ions in the lattice is going to be smaller. Okay, so that is the way I would think about how to explain differences in lattice enthalpy. Okay, finally, before we finish up here, let's compare what I'm putting in this table here, magnesium chloride and magnesium oxide. Right, magnesium oxide has got a whopping 3,791 kilojoules per mole lattice, a really big lattice enthalpy. And we can probably explain why, can't we? Because what are the ions in the magnesium oxide? It's Mg2+ and O2-. So if you think about our equation, F is proportional to Q1, Q2 over R squared. Well, in the case of magnesium oxide, we've got +2 times -2. So that's going to be Q1, Q2 is going to be 4 times bigger than it would be in sodium chloride, isn't it? Yeah. So that makes a big difference. And also, compared to sodium chloride, well, the magnesium ion is small, and the oxide ion is also small. So that means R is going to be small in magnesium oxide, and that's what gives this really very high lattice enthalpy for magnesium oxide, 3,791. Okay. Right. Before we finish off, you can. I've explained these mostly. Sorry, I've explained these mostly in terms of this equation, haven't I? The this equation up here, and I think that's the easiest way to do it. What you can do as well, you can say, right, you can talk about charge density. Okay. Which I don't think I would do. People tend to get confused with that charge density. You can say, right, if you compare magnesium oxide to sodium chloride, say for example, well, the charge density of the magnesium ion is much higher than the sodium ion because it's 2+, not just 1+, and also it's quite a bit smaller, so it's got higher charge density. Oxide ion again has got a high charge density because it's 2- and it's small compared to the chloride, which is 1- and quite a bit bigger. And so the the charge density is stronger in magnesium oxide, so you get a stronger attraction. You can explain it that way, but again, I would probably like to explain it using this equation here, and you can forget about the constant, but you don't have to remember what that is. Just remember F is proportional to the positive charge times the negative charge divided by the separation squared.